Hello, this is a continuation of the tutorial on BSL section 10.7. And before we proceed with solving the case of the rectangular fin over here, I'd like to make a connection between the rectangular fin and a more general case. So in general, the cross-sectional area of a fin is not constant, and the exposed surface area of the shells as we're doing the shell balance is also not constant. So for example, if you look at a handout that's uploaded on Canvas, Chemi 103A Bessel function handout, it starts out with the usual Bessel function, then the modified Bessel function. Then it goes to an example, and that example is for a circular fin. And it's a great example for seeing how the cross-sectional area and the differential ring of exposed area on the top and bottom can both change with distance from the heated wall. And on the homework, you'll be asked to do a problem where you have a tapered fin. And that is another case where you have the cross-sectional area changing with distance from the wall. But the exposed surface area of each differential element remains constant. I'd like you to go through the analysis in section 3 of the handout before you take a crack at the tapered fin, unless you're already really familiar with Bessel's equation and Bessel function. So let me say a few words more about this. So if you have a cross-sectional area that's changing, you'd want to do the shell balance a little bit differently than we did last time in the first half. So if you look at the net input of energy, in minus out, into a shell of a fin. So previously we drew a rectangular fin, but now suppose we have a cylindrical fin. And we have an area where heat is coming in by conduction and an area where it's leaving by conduction. And in addition, we have exposed surfaces where it's leaving through the top and the bottom, such that the total energy coming in, the rate of input, adds up to the sum of the outflux continuing down the fin and the sum of the energy that's being lost to the surroundings. And in this case, it's treated a little bit like the electrically heated wire. So in this case, we're treating the conduction as if it's only going in one direction. And we're not treating the two-dimensional character of the temperature field inside the fin, because fins are made of high thermal conductivity materials and they're thin. And the combination of those two things makes it so there's very little gradient. So instead, it's taken as kind of a negative generation term, consumption term, where the energy is leaving out through the surfaces, and that is simply taken as energy disappearing from this solid ring. So let's see. So in minus out plus generation is accumulation. Okay, we're considering steady state, so the accumulation is 0. And the in minus out, we have a radial flux here through a cross-sectional area that can depend on R. And we're evaluating that at Z, so energy per area per time times an area energy per time entering. And then we subtract the similar term, but evaluated at, let's see here, I'm mixing up the problems. So this would be at R, and subtracting off the contribution at R plus delta R. And the generation term, so it's a consumption term, it's a negative generation term. Uh, you have energy leaving through the top and the bottom surfaces, so that gives a factor of 2. And you have an area that here is 2 pi r, so I called that the perimeter, times delta r. And that gives the area of this top surface. And then you have the same on the bottom. So we have a perimeter. And in fact, what I may do is I'll call this a differential exposed surface area, DAS. That's the notation you'll also see in the handout section 3. So that's the area of the exposed surface on the top. Factor of 2 is because there's one on the bottom. And then you have a rate that energy is being removed to the surrounding fluid. So a heat transfer coefficient times the temperature difference between the surface at that radial position. Oops, same thing. Let's see, minus the temperature of the fluid in the bulk far away, and that sums to 0. Okay. So let's see here. So if we take DAS dr times delta r, so this is another way to look at the perimeter, and this is the notation used in the handout section 3, then it will allow us to divide through by delta r and take the limit as delta r goes to 0. So we'll have this. And that will give us right. And let's see, so in the handout, section 3, you'll see how this, as you turn the crank, follow it forward, it'll lead to a modified Bessel's equation. That's the same kind of equation that you're going to encounter on problem 4 of this week's homework. So please take a look at the steps involved in getting it to the form of a modified Bessel equation and how the solution works out. And it'll give you a leg up on handling the tapered fin. Good. And so now returning to the rectangular fin. So in our case, the cross-sectional area is just the thickness of the fin, which is 2b. Times the width of the fin. So this is 2b times w, and it's constant. Okay. And then the differential area exposed on the top is, in this case, right. So we have delta z, the z direction, and this area is then just the width times delta z. So Cool. And then so DAS, it's Z in this case instead of R, is W, and right. So we will have minus 2BW dQR, R. So here it's Z, dZ, and then minus 2 for the top and bottom faces times W, dZ is already over here, H T minus T infinity, and that sums to 0. Okay, so in this simple case, and I think this is the equation we left off with at the end of the preceding video, W's cancel, 2's cancel, and we can introduce Fourier's law. And Fourier's law is universally a great approximation for heat fins because they're made of materials that have high thermal conductivity that's uniform through the material. Okay. Fourier's law, so we have that hit there, and we will end up with, okay, let's go plus, so minus, okay, good. And we're treating that as constant. So it comes out of the derivative, and then we still have minus H over B. And we'll divide through by K. Okay, so we have second order ODE. We have boundary conditions, so it's second order in Z. And so we need two boundary conditions. We have one that's clear cut. You almost always have a specified temperature at the wall, which usually is taken to be the highest safe operating temperature for the device you're protecting. So you have a specified temperature boundary condition at Z equals 0. We'll call that T wall like they do in BSL. And at Z equals L, you usually don't have a specified temperature. The only case in which you would have specified temperature is if you deliberately made the fin really long and the temperature at the end agrees with T infinity, but you would never want to do that because it's very wasteful. The other possibility is to go ahead and apply Newton's law of cooling like you did on the top and bottom surfaces, and apply that also to the tip of the fin, the far away edge. But there's a simplification that's usually very good. So as you recall, looking at the photos of actual heat fins, the area of the end is very small compared to the area of the whole fin. So even though in principle there can be a flux from that surface, it's negligible. And so that gives a simplification where you treat the flux out the end as if it were insulated, because that flux in fact is so small that it doesn't really matter. So you have QZ is approximately 0 at the end. And so we have DT DC is 0. So this approximate means negligible. Doesn't mean it's exactly 0, it just means a good approximation. Okay, so, right. So we have this second order ODE, we have our two boundary conditions. We look at the structure of the differential equation, and it reminds us of something where you would have a second derivative equals some coefficient squared over here times that function itself. Actually, to make that more explicit, let's go ahead and let's define theta to be t minus t infinity. And then the differential equation fits nicely and clearly into this form, which gives solutions that are growing and decaying exponentials. And you differentiate it twice, brings out 2 powers of m. You have this coefficient out here that's the square of the multiplier on z. And so that suggests that we define m squared to be h over bk, or m is the square root of h over b times k. So if we do that, it makes the math very convenient, easy to write out. I make fewer mistakes. And if we take theta to be t minus t infinity, then at z equals 0, then theta at the wall is just t wall minus t infinity. And d theta dz equals 0 is still, it's now dt dz equals 0 is unchanged by this definition of theta as t minus t infinity. Okay. All righty. And so I'm going to take you through the solution of this problem in terms of exponentials. And then I want to show you a slick trick that makes it a super clean and simple solution if you use cinches and coshs. So to appreciate why that's nice, it's nice to go through the somewhat grungier one first. Okay. Right there. Okie doke. So, knowing that the solution is going to be growing and decaying exponentials, the approach that seemed obvious to me was to try to introduce theta of z is the sum of the two independent solutions. And so this is what I'm going to show you first. But you could equivalently go directly to theta z is equal to, I'll call this a capital C1 cosh mz plus capital C2 cinch mz. Okay. So we're going to do this one first. And when we impose the boundary condition at the wall, okay, at the wall, z equals 0, so the exponentials are just 1. So if C1 plus C2 equals theta wall. Okay, so okie doke. And then, right, boundary condition at z equals L gives, so here we're taking the derivative of theta, brings down a power of m and a power of minus m. So we have C1 factor m e to the ml minus m C2 e to the minus ml equals 0. Okie doke. So we can massage that around to get C1 equals C2 times e to the minus 2 ml. We can introduce that in up here and get that. So theta wall is C1 times 1 plus Oh wait, I did a little differently. I factored out the C2. Right. So 1 plus e to the minus 2 ml is theta w, and then we can solve that for C2. So substitute this one in here for C1, solve for C2. And you get C2 is theta wall over 1 plus e to the 2 ml. And C1, so look at that. So C1 is theta wall, oops, sorry about that, e to the minus 2 ml over 1 plus e to the minus 2 ml. Got it. Okay. What comes from there? Great. So now we put those back in and do a little bit of algebra, and you get that okay, let's see if that looks good here. So I've taken the theta w down over here. We have an e to the minus 2 ml times mz, and then we have here just a 1 because the theta w is up there. That's all good. And then if I multiply numerator and denominator by e to the ml, I'll have e to the minus ml plus mz. So it'll be e to the, let's see here. So we're multiplying numerator and denominator by e to the plus ml. Okay. So we have e minus 2 ml. I got that wrong. Okay, and so that's one way to solve it. And takes a bit of, just grunge. And sadly for me, when I do a lot of grunge, I tend to make a lot of mistakes. So I don't like grunge. And so I wanted to show you a slick trick. Okay. Alternatively, so if we work in terms of cinches and coches, so I always have to sketch these out to remind myself what they look like. Okay, so suppose we have cosh. It starts out at 1, and then it goes up just a little. And we have cinch, and it is 0, crosses 0, has a slope of 1, and then comes and hugs this one up there and looks kind of anti-symmetric down there. So here we have cosh, and here we have cinch. And one of our boundary conditions is 0 slope. And as we've formulated the coordinates here, that boundary condition is imposed at a non-zero argument at z equals L. But we say, hey, cinch never has a slope of 0. Cosh has a slope of 0, and it's at the origin. It's at the argument equals 0. Can we move our boundary conditions around, flip them, so that we have Cosh at 0, satisfying us that 0 slope boundary condition? Okay, let's try it. So currently we have a fin, and out at z equals L, we have dt dz equals 0. And over here we have a specified temperature. Theta equals theta L. And then this one is d theta is equal to 0. Huh, okay. What if we do a change of coordinates? How about we try introducing a coordinate c that I define as L minus z. Why do I do that? So that I move this boundary condition to c equals 0, and then clearly Cosh is going to be the solution and Cinch isn't, right? So that's a nice way to frame the problem. Let me get rid of this, just give myself some space. And actually, we don't need this diagram anymore, I don't think. Okay, so let's just move this up so we can do some work here. And so this was at z equals L. So now it's going to be d theta dc equals 0 at c equals 0. Right, and so when you differentiate by c once, you actually would have a minus sign, but since the other side is 0, you don't even notice. Okay, and then over here, this boundary condition will now be, substitute in z equals 0, this boundary condition will be at c equals L. Okay, so we just flipped it around. This means that when we do our general solution, so we have theta is script C1, Cosh. Am I glossing over something here? A little bit. Okay, here, let me go back. So in terms of z, our differential equation was d squared theta dz squared equals m squared theta. If we do this change of variable, a single derivative would flip it to a minus sign. But since we're differentiating twice, the equation is still going to have the same form. So we'll have d squared theta dc squared equals m squared theta. And that's why I write the same general solution. So you have theta is big C1 Cosh of C plus big C2 Cinch of C. Okay, and we look at our boundary condition at c equals 0, and that gives us that C1 is non-zero and C2 is 0. And then we have our boundary condition at c equals L, so theta equals theta W. And that's going to set this coefficient C1 such that this equals theta W. Okay. That's going to work. Okie doke. Oops, I did missed. Please forgive me. forgot the values of M. They go right there. And voila, we can switch our coordinates back, and we just get and this is a much quicker path to the solution. So it took advantage of remembering some of the properties of the hyperbolic functions and saying, oh, I could flip my coordinates, why not? And then solving it in an advantageous coordinate system so that the determination of coefficients is like that. Okie doke. So now the next thing you want to do is check and see if you think your solution makes sense. So that's the next thing you want to do. And here, grab this. So yeah, the next thing you want to do is make sure that the solution makes sense. So what's the first thing we usually check? Dimensions. So we want to make sure it's dimensionally consistent. So, so before using an equation, you always want to make sure that don't catch any obvious mistakes before actually using the model that we've just solved. So we'll take a look at three things. One is it dimensionally consistent? And we find that it is. So we have so this part is dimensionless. And then both of these have dimensions of temperature. And so in this case, checking that it's dimensionally consistent is very quick. And then the next thing you want to check, I don't know if this is the order you would do it, but one of the things I wanted to check is, does the shape of the solution make sense? Does it make physical sense? And so I'll just put down shape of the function. Does it make physical sense? So let's go ahead and again sketch cosh. Okay. And so we have this nice function, shaped like a bowl. Okay. And our solution, let's see, if we look at it in terms of C, so let's suppose this is MC, which is the argument of cosh in our solution, and we have cosh of MC up here. So in terms of MC, there's no gradient. At the tip of the fin. And we like that. Then at the wall, the hot wall, that's where C is L, right? L. So the argument there is, we do some vertical line here, drop this down. This would be at ML corresponds to the wall. And the wall is hot. And sure enough, this is higher. That's good. And steeper. Okay. So it gets steeper and steeper as it goes out. That's okay. That also makes sense. All right. So then the next thing I would check is does the effect of the parameters in the problem on the solution make sense? Okay, so let's look at the effect of parameters in the problem. So there we have a couple. So one is, does the temperature of the wall and the temperature of the fluid far away enter the problem in a sensible way? And then it's useful to shrink all this stuff down. Try and keep this together. Okay, so our solution in terms of theta is t minus t infinity, and that equals theta w, which is tw minus t infinity, multiplied by cosh of m L minus z. And recall that m is h over bk square root. Okay, so it does make sense that the prefactor here has a magnitude that spans from Tw, the hottest temperature, the wall, to T infinity, the temperature of the fluid. And so the bigger that difference is, you'd expect the whole temperature variation to scale up and down with that. So that seems reasonable. Then imagine if we held L fixed. What would be the effect of varying H, B, and K? So, so we have H, B, and K. So let's think that through. So if we have a fixed L, imagine fixed L. If H increases, then this point here along the MC axis, so along this axis here, if H increased, you'd move further out. And if H decreased, you'd move further in. So that's the direction of increasing H. And so that means that as H increases, you have a bigger temperature difference between the wall and the end of the fin. Does that make sense? So if you need to just hit pause and think on that for a second and see if I have a higher heat transfer coefficient, would my temperature drop further down before I get to the end of that fin? Same length fin, same properties. I think you'd say, yeah, that's good. And then how about this one? Might be a little bit more puzzling. So if I make the thermal conductivity higher, I keep L the same, and now I keep H the same. I'm just changing the conductivity. I make the conductivity higher, and it moves in this direction, moves in the opposite direction. So it goes this way. That means I'm making the temperature profile flatter. So this temperature is being rescaled so that it's always agreeing with the temperature of the wall. But the magnitude of the temperature drop before you get to the tip of the fin is a smaller drop. So again, you can hit pause if you want a minute to think about why that would be. And then I'll blurt it out. So if I make the thermal conductivity higher, the conduction is faster out into the fin, and it keeps moving that heat out, keeps that temperature difference very small, because the higher the conductivity is, the smaller the gradient required to move that energy out. And then it's removed from the surfaces of the fin to the fluid. And Similar thing happens if you make B a little bit thicker, then it maintains that temperature further out into the fin, and the overall temperature drop goes down, and the actual energy you're removing per area fin actually goes up. Okay, so now we've checked the dimensions, we've checked the shape, we've checked the way the parameters of the problem enter, and we feel good about this solution. So now we want to use it for something. So why did we go about solving this problem in the first place? Okay, so we wanted to be able to do design. We want to be able to design heat fins. And design usually involves a trade-off between things, right? So we know we need to get enough energy out to protect the engine or the transformer or the chip. And on the other hand, we don't want to put on too much metal. If it's a mobile vehicle or a portable electronics, you don't want to add weight, and you don't want to waste resources, and you want to give people the most value for their money. You don't want to add cost without a benefit. So you want to be able to get the heat out, but not a whole lot extra metal to do that. So here, let's see. Okay. So what is this solution good for? So on one hand, we want to know how much energy are we now getting out by adding fins compared to what we would have gotten out if we didn't add fins. And in particular, suppose you're protecting the CPU chip, you could calculate at what rate can I remove heat if I allow it to get to the maximum safe operating temperature. And then I find out that I'm dissipating 10 times that. What am I going to do? I'd like to have a design tool that tells me how big the fins are for all the for given material properties and so on, to get me that 10x more that I need. So one thing is, what is the effectiveness? So the effectiveness of the fin. Okay, so that is called the fin effectiveness. And so we have a ratio where the numerator, so we have epsilon F for effectiveness of the fin. The numerator is how much energy we're actually moving out through the fin. And there's two ways to calculate it, and they both give the same answer. One is the flux through the base of the fin multiplied by the area of the base of the fin. And the other is the integrated energy really moved to the fluid through the top and bottom surfaces of the fin. Two different ways to calculate it. They both give the same answer. I vote for doing the first one because we can just differentiate this function and multiply it by an area, and we'll have the answer. So let's see here. Right. So Q with the fin over Q without the fin. And without the fin, we only have that small area that's the footprint of the fin. Right. And that cross-sectional area, and here I'll go ahead and just write it as it would be for here. So 2b is the height, w is the width, that's the area through which the energy would be transferred with no fin. That little bit of surface would be at the hot temperature of the wall, and there'd be a heat transfer coefficient describing the fluid properties and the way it's flowing. moving that heat out from T wall minus to a fluid that's at temperature T infinity. And then in the numerator, we have the flux through the base. So the base has the same area, 2BW. And the, uh, the flux is given by Fourier's law. So we have minus K dt dz evaluated at z equals 0. Cool. That's the amount of energy that's now going through that same area because it's being conducted out and then transferred to the fluid out on the fin. Cool. So we have our expression for T as a function of the parameters in the problem. So, and we want to take dt dz. And there's a minus sign over here, and we want a minus sign over there. So they're going to end up canceling. When I move it up there, right here. Okay. Take this derivative, we're going to get a factor of minus m. This will become sinh. Over cosh. Good. So this is playing fast and loose there. Okay, we're going to be evaluating this at z equals 0. If we evaluate this at z equals 0, we'll have tanh m. Okay. We're going to substitute this in up here. The minus there is going to multiply this minus there, and we'll have plus km tw minus t infinity tanh ml. So let me shrink a bunch of this stuff, give myself a little space here. And so the numerator is going to have 2BW. Minus signs are going to cancel. I'm going to get K times this M times tanh ml and multiplied by this TW minus T infinity. Okay. I threw 2BWH, TW minus T infinity, and so we can start canceling stuff out. Those are going to cancel. 2BW is going to cancel. We're going to have Km over H, where M is square root H over BK. Put that in up there, and the K's are going to, I have a full power on the numerator and a half in the denominator, so I'm going to have a root K in the numerator, and then I will have a root H in the denominator and root B. Okay, so that is going to give me this factor out here. I'm going to have K H B square root that. Okay, so what is that going to look like? So this is my effectiveness factor. So tanh, this is probably worth the diagram too. So tench, what's tench look like? Okay, so tench looks like this, and then rolling off, it gets really close to 1 around 2.5. Okay, so we've got 1, -1, and so here's the tench. Okay, so our fin effectiveness it has the leading factor that is K over BH to the 1/2, and then we have this tanch. And no matter what I do here, I can never make tanch bigger than 1. It just asymptotically approaches 1. Make sure my drawing is okay there. Okay, so you're asymptotically approaching 1. So this can never give me an effectiveness that's, say, 10. So it's usually significantly bigger than 1. Okay, so the only way that I can get an effectiveness substantially bigger than 1 is to have this prefactor be substantially bigger than 1, right? So high effectiveness requires high thermal conductivity, and you only get the benefit of heat fins if you have low heat transfer coefficients. And then, right, a thinner fin tends to give you a higher effectiveness. So, and so when we look at a situation where, say, we have a chip, it's dissipating 10 times more energy than I can move through its superficial area, then I can start thinking about, well, what is the heat transfer coefficient that I have, and what material should I make it out of so that I have the chance to get that factor of 10 that I need. Now, the other thing is then, because then this would just tell me, you know, ballpark what I should make it of, how thin it should be, and then I could just make it go off to infinity, make it as long as I want. Except that that's a waste. The measure you need to decide whether or not to make the fin any longer is something that's called the fin efficiency. So let's see, let's push all this down. That's effectiveness, fin effectiveness. And then fin efficiency. So the fin effectiveness gives me an idea of how much more energy I can move with a fin. And the fin efficiency says, how much of that fin am I actually using? What's the portion of that additional metal that I'm putting on there that I'm actually getting benefit from? So this one, it's eta F, fin efficiency, and it's the Q with the fin over the maximum possible with that fin. So the maximum possible for given fin is to have the entire fin at the temperature of the wall. And so you have the actual energy moving through the fin, which we can pull over here. That's good. So that's my numerator. And let's see, the denominator, maximum possible. That's the whole area of the fin. So we have 2 for top and bottom, width times length, total area, heat transfer coefficient, times if the whole area was at T wall, transferring energy to the surrounding fluid at T infinity. So now this one, I'll switch this around a little bit. So this we have, I'll put 2WB so that we can strike through the W's and strike through the temperatures. And then we have KM, LH, is that agreeing with here? Let's see. Okay. Tighten this up a little bit here. Okay, so we have BK times M, where M is H over BK to the 1/2. Okay, so that's going to cancel out a half power of the BK in the numerator. So we'll have BKH whole thing to the 1/2 times tanh of ML over, down here we're going to have H and L, and that's all. Is that right? Yes. Good. Right. So in the numerator here, we had BKH to the 1/2. We have an H down here. So we're going to have BK over H to the 1/2, which is 1 over M. And so this simplifies to simply having, well, figure out how to, so it simplifies to tanh ML over ML. And let's think about what that function looks like and if it makes physical sense with the fin efficiency. So tanh ML at small arguments, tanh of, like if this axis is ML of ML, at small ML, it approximately equals ML. And that means that at small values of ML, eta F is 1. So for small lengths, for example, if we think of L being small, compared to 1 over m. So the product ml is small. Then we've added on this little bit of fin, and all of it is at T hot, to the temperature of the wall. And so it's 100% utilized. So eta F is 1. Makes sense. Then as we go further and further out, as we go to large ml, then we have tench just approaches 1. Okay, so you have right. So the numerator approaches 1, and eta F starts falling as 1 over ml. Okay? So let's see what does that look like. Okie doke. So generally you want your heat fins to be well utilized. So if you aren't up at where the value of eta F is 1, you're not going very far down. So as one rule of thumb, you will rarely find a fin where m times L is greater than 3. You won't find that. Okay? And then similarly, it's not a good use of weight on a vehicle or weight on a piece of portable electronics. So you won't find L so long that it makes ML greater than 3. Okay, so usually you'll find ML less than 3. What does that mean? So L less than 3 over M. M is H over B times K to the 1/2. Okay, so So if the heat transfer coefficient is really abysmally small, then it makes sense to have a relatively longer fin. You'll be getting benefit out of it because the heat transfer coefficient is so low, the temperature is staying hot out into the fin, so you are getting the benefit of the fin. Okay, so H small means it still makes sense to have a long, the length of the fin that is beneficial goes up. If K goes up, then again, you're getting better at bringing the heat out into the fin, and so you get benefit from a fin out to a longer length. And so that's kind of a rule of thumb for where you would the range of fin lengths that would be reasonable to try, and you'd still get pretty good use out of the fin. Okay. So now we have two tools for design. One, to help us figure out, is it possible for us to get as much energy as we need to get out? Is it possible to get it out? Based on the choice of a material, does it have high enough conductivity? And then the geometry, and in view of the heat transfer coefficient. So that's the effectiveness, epsilon sub F. And then that criterion basically guides us toward a material and maybe dimensions, but it won't tell us how long. So the thin effectiveness, I said that wrong, efficiency, so how well utilized is the fin, gives us an idea of how long we should make it, and don't go longer because you won't be getting a good enough bang for your buck. Okay, now is that enough to give you what you need for the homework? I think so. So I will wrap up there, and I have a little bit more material on fin arrays and whatnot, but I'm not sure if it's needed for the homework. And meanwhile, we have other topics that we need to move along to. So I hope this was helpful. It provides a lot more information than what you find in BSL, and helps you link up what's in the handout with what you'll be doing on the homework. Great. So I hope you enjoy thinking about heat fins and noticing them in your life, and potentially designing them in the future. Well, thank you very much, and talk to you again soon.